So hi everyone, welcome to our last talk of the semester. And again, in case there are some new audience here, this talk series will be given by the awardees of NCU-Delta Young Astronomer Lectureship, which was founded by the National Central University and the Delta Electronics Foundation to recognize young scholars who have made outstanding contributions in this field. So each year, the awardee will be invited to Taiwan and to interact with the local astronomers and the public. So I think the first award was given in 2012. And the original plan for this year was to invite all the previous awardees to come back to Taiwan, but unfortunately, we have to make this event online due to the pandemic. So our speaker today is Professor Stephen Smartt. I think Stephen received this award in 2012, which is the very first awardees of this lectureship. And now he's a professor in the Astrophysics Research Center at the Queen's University, Belfast. And he's a world expert, especially in studying the depth of massive stars and supernovae. And he has led many, I think, important projects such as Pan-STARRS in the Survey for Transient and PASTEL project, which has classified thousands of transients so far. I remember I was also part of that project, when I was a graduate student. I was also, just recently he has started another ambitious project called ENGRAVE, which is dedicated to follow up the electromagnetic counterpart of gravitational wave detections. So it's really our great pleasure to have him here. So today he's going to talk about the present and future of multi-messenger astrophysics. So just a few announcements before we start. Please mute yourself during the talk. If you have any questions or comments, you can leave them in the chat box anytime you want. We will try to come back to those questions in the middle of the talk or during the Q&A session after the talk. So, all right, Stephen, I'll let you take this away if you're ready.
Thank you, Yan-Chen, and it's a pleasure to talk to you. I'm just sorry I can't be in Taiwan this time. Hopefully, in the not too distant future, we'll be able to travel and I'll be able to make the trip there. But thank you for the opportunity to talk to you again. I'm going to talk about the present and future of multi-messenger astrophysics. It's an area which has just started really in the last few years. Yan-Chen suggested I give a very broad overview for the first five or 10 minutes and before I start my talk properly. So let me give you an overview of and I'm going to talk about some of the projects which are listed here that Yan-Chen mentioned, but let me just give you a general introduction to the transient sky and the new developments which have taken us beyond photons in detecting objects, transient objects in the universe. And beyond photons, I really mean gravitational waves. There have been detections of high energy neutrinos from the ice cube detector at the South Pole. I won't talk about those in this talk, but I'll focus on gravitational waves and combining photons with the detection of gravitational waves. I came to Taiwan back in 2012 and was fortunate enough to be given the award that Yan-Chen described. And most of my work at that time, up until the last few years, has been focused on the transient sky from the optical perspective. So finding extragalactic transients, mostly supernovae, but some which are unexplained, for which the physical mechanism to produce the luminosity does not appear to be or is difficult to describe with the normal supernovae mechanisms. That is core collapse in a moderately massive star, and a type 1a supernova, which is the destruction of a white dwarf. But here's a very nice movie put together by Isaac Shivers at UC Berkeley, and it shows the transient extragalactic sky from 1,000 years ago when humans first started observing and recording the transient sky. And these are all supernovae or supernovae-like transients in galaxies outside the Milky Way. And much of my work has focused on this in my career and certainly the last 10 years. But the big developments in the last 4 years, well, before I get there, just to point out that there are about 83,000. This was in July this year. I did this count. It's gone up significantly since, but there are about 83,000 known and recorded extragalactic transients from different surveys around the world that record their the objects that they think are true transients outside our galaxy. Again, they're mostly supernovae, they're mostly the normal supernova population, and these are recorded currently by surveys such as ZTF, Pan-STARRS, the Gaia satellite, Atlas, which I have a significant involvement in, and Assassin, which focuses on the bright end of the supernova population. But there are about 83,000 optical transients registered with the IU and given formal IU recognition and names, and that's probably up to about 85 to 90,000 now. And so with these numbers, it becomes interesting to look at the extremes of the population, what objects we can find that don't fit the normal paradigms of supernovae, of core collapse of massive stars, and type 1a supernovae from white dwarfs. The universe's densest objects tend to drive, so this picture of the transient universe is driven by either the formation or the explosion of compact objects. So normal supernovae from massive stars form neutron stars. Their core collapses, and the core will form a neutron star, and that gravitational potential energy, which is released when the core collapses to form a neutron star, drives the explosion. White dwarfs produce type 1a supernovae when they become unstable and they shrink, their temperature goes up, and they end up in a thermonuclear runaway, and carbon and oxygen burns to radioactive nickel, which drives the explosion. And black holes are almost certainly formed in some types of stellar transients. Exactly which ones we don't know for sure. Probably in the formation of long gamma ray bursts and their associated supernovae. But there may be other transients that form black holes that we haven't quite identified yet. But these are the universe's densest objects, and these also produce, as we'll see, gravitational waves when they are in binary systems. But this densest form of matter, if we compare them just in a broad sense, white dwarfs have a density, so they are the size of the Earth, the radius of the Earth, and about 1.4 solar masses squeezed into the radius of the Earth. That's the most massive white dwarf. And they would have a density of 10,000 kilograms per centimeter cubed. So think of a teaspoon, and 1 teaspoon of white dwarf matter would weigh 10,000 tons. For a neutron star, that is similar sort of mass to a white dwarf, the maximum mass of a white dwarf, so about 1 to 2 solar mass, 1.4 to 2 solar masses. But that material is squeezed down into a 10-kilometer radius. That's approximately the radius of a neutron star. So that means the density of material, the amount of material on a teaspoon, is 6 times 10 to the 11. So imagine everyone on Earth squeezed onto a teaspoon. That's the density of neutron stars, the density of an atomic nucleus. And then black holes, well, we're not sure exactly what the form of matter is within the event horizon of a black hole, but if for an object which is greater than 2 solar masses, the black hole of something around 2 solar masses or greater would have a radius, a Schwarzschild radius of around 5 kilometers. So something which it would have an effective density higher than that of neutron stars. So it's the formation of these dense objects that really produce the transient universe. Either their formation produces a transient, or their destruction produces a transient. So the next, the recent development, it's very exciting development in this field, was in 2015, when black holes, presumably produced by supernovae in some way, were detected by gravitational wave detectors, LIGO and Virgo collaboration. The first one was detected only by the LIGO detectors in the US. These were surprisingly very massive black holes, a 36 and a 29 solar mass black hole discovered in 2015, which were orbiting around each other, and their final in-spiral and merger was detected by LIGO. The whole event only lasted about 0.1 of a second, but it was an extremely loud and high amplitude event detected in the gravitational wave interferometers. The Nobel Prize was awarded for this in 2017, and this opened up a new window in the universe for us to combine the gravitational wave signatures with photons. And the next big development in this field was just 2 years later in 2017. So several black hole mergers were detected between 2015 and 2017. And in 2017, then the first binary neutron star was detected at a surprisingly close distance of only 40 megaparsecs. At the time, a short GRB, a weak short GRB was observed, both by Fermi and Integral. And the spatial location of the GRB from triangulation of Fermi and Integral, combined with the sky map from the gravitational wave detectors, pinpointed this relatively small area on the sky, only about 40 square degrees, 30 to 40 square degrees. And what several teams around the world did, they looked in this area of sky and they picked out the 20 largest galaxies and searched those galaxies for any optical transient. And in one of them, NGC 4993, a distance of 40 megaparsecs, an optical transient was found that hadn't been seen before in surveys of the sky up to that point. Here's the host galaxy, and here is the source which created the gravitational wave. So this is the optical source pinpointed exactly to its host galaxy. This caused the gravitational wave GW 170817. And this gravitational wave event from two merging neutron stars produced what we call a kilonova. And a kilonova is labeled because it's about 1,000 times more luminous than a nova. And this image was taken by Janet Chen with the Grand facility at ESO. And there you can see an object which started very blue and became red, which I'll talk a little bit more about. But this is pinpointing the first, for the first time, a source of gravitational waves. Two neutron stars merging, and only about 1 or 2% of the total matter was ejected, but that was enough to create this optical transient. It faded very rapidly. We've never seen anything like this before. It faded. It was reasonably luminous, but it faded very quickly over a period of 10 days. So that was 2015, detection of gravitational waves from merging black holes. 2017, detection of the first neutron star merger by LIGO and Virgo, and detection of the first kilonova associated with neutron star mergers. But that's now 4 years ago. So what have we learned and where are we going in this field? That's the end of my introduction for now. I'll just pause just to see if there are any questions.